Welcome everybody. Today title of the presentation is Spectral Meets Simplicity, Unlocking Spectral Cytometry with CytoFLEX Mosaic. This presentation is the result of an amazing collaboration between Beckman Coulter Life Sciences and the Leiden University Medical Center. And me and Tamar today will walk you through our findings. This document contains confidential and proprietary information owned by Beckman Coulter Inc., and any disclosure, use, and copying or distribution of this information without the express written content of Beckman Coulter Inc. is strictly prohibited. My name is Fanuel Messaggio, and I'm a senior application scientist at Beckman Coulter Life Sciences, and I'm excited to walk you through a key segment of our presentation focused on the evolution of the CytoFLEX platform and the introduction of the CytoFLEX Mosaic Spectral Detection Module. Beckman Coulter has a long legacy of innovation in flow cytometry, and we have a global presence with 11 operation locations, 3,400 associates, and more than 300,000 systems installed globally. From the APX2 in the 1970s to our most recent advances, each milestone reflects our commitment to user-driven solutions. Our platform have evolved from an early single laser system to today's modular high-dimensional analyzer. The CytoFLEX platform launched in 2015, and that marked a pivotal moment, combining high sensitivity, compact design, and intuitive usability. And our journey continues. Introducing the CytoFLEX Mosaic, where spectral meets modularity. Over 10,000 labs globally rely on the CytoFLEX family, from the nanoscale CytoFLEX Nano to the 6-laser CytoFLEX LX. Researchers choose their instrument for their flexibility, robustness, and consistency. The CytoFLEX Mosaic module takes this foundation to the next level by bringing spectral capability to our existing analyzers. Compatible with both CytoFLEX S and LX models, it allows users to switch between spectral and true conventional mode based on their experimental needs. This dual capability is designed for versatility, and you don't have to choose one over the other. This combination of modes enable you to optimize filters, fall back on conventional if spectral needs troubleshooting, and reproduce experiments using two different detection systems. It enhances flexibility, reproducibility, and confidence. Technically, the Mosaic module connects via a 1.8 meter cable, allowing flexible placement in your lab, beside or under the main unit. The fiber optic cables are manually repositioned, and the connection have been stress tested for durability. The feedback for our beta tester have been overwhelmingly positive. For example, Dr. Domenico Lotartalo at the University of Modena shared how this integration eliminated the need for multiple instruments and simplified this workflow. The software is another major advantage. CytExpert for Spectral is intuitive and familiar to those already using conventional CytExpert. It offers user management tools, compliance feature, and offline planning, all without a dongle. These are a few screenshots of how the software looks like. The software includes Smart QC feature. It alerts you to saturation level and mixing gaps, helping you fine-tune experiments in real time and ensuring the integrity of your data. CytoFLEX Mosaic is more than a module, and we have integrated with FluoroFinder, giving you access to instrument-specific panel building tools and antibody databases. This reduces trial and error and speeds up experimental design. From the Beckman Coulter website, you can redirect to FluoroFinder with just one click. For downstream analysis, we have partnered with Cytobank. Its powerful machine learning and data visualization tools help researchers unlocking the full potential of spectral data. One of the latest upgrades for spectral flow cytometry was default scaling, setting to help with challenging data. These are all the configurations that allow you to upgrade to a mosaic from your CytoFLEX. The data that you will see in the next slides have been generated using a CytoFLEX Mosaic LX configuration, features 6 lasers, 88 detectors, and emission detection from deep UV up to 950 nanometer. Side scatter detection on each lasers and enhanced unmixing capability make it possible to clearly separate highly similar fluorochrome and extract autofluorescence. Altogether, the CytoFLEX Mosaic is more than a module. It's an adaptable, high-performance upgrade to an already trusted platform. It gives the lab the flexibility and power to push their research further with greater clarity and control. And now, I have the pleasure to introduce my collaborator, Dr. Tamar, head of the Flow Cytometry Core Facility at the UMC, who will walk you through the application side of the mosaic in a real-world core facility environment. Thank you.
So thank you, Fanuel, and thanks everyone for watching. So first of all, there's also a disclaimer from my side, and basically it means that the rest of the presentation is all my opinion, but it also means that, Beckman Coulter is not responsible for it, but it also means that it is really my opinion, and Beckman Coulter did not have a say in what I would be presenting. So first of all, our core facility, so it's been established in 2017, and it's a fairly large facility. So we have 25 instruments. Last year, we saw over 500 users and more than 20,000 hours of bookings on our instruments. And what I think is the most important part of the facility, that's the team. And we have an absolutely great team. They take care of starting up instruments, doing troubleshooting, but they also train a lot of users, give seminars, we organize user group meetings, and we provide some assisted sessions as well for sorting and for site-off, and we do a lot more. So our relation with Beckman Coulter started when we acquired 2 CytoFLEX SRT sorters. So we have 2 4-laser 15-color instruments in different labs. But I think what is more interesting for this presentation is that we also have a lot of spectral instrument at the facility. So we have 5 Cytec Auroras, we have ID7000, and recently acquired FACSDiscover S8 as well. So we have a lot of experience with a broad range of instruments, and in total, since 2019, we trained over 450 users. So we're also very experienced in training our users for this. So that actually, the collaboration with Beckman Coulter and our experience with spectral cytometry led to Beckman Coulter asking us to beta test their CytoFLEX Mosaic. And in this case, they asked us to test the so we got a early model of the 6-laser CytoFLEX LX coupled to the Mosaic 88 Spectral Detection Module. And Fanuel already told you a little bit about this, but I just want to highlight, so it's a 6-laser instrument with 88 detectors. And I think this image shows the configuration of the instrument. And in gray, you see all of the detectors of the CytoFLEX LX, which are just small stops, small parts of the spectrum. Whereas in red, you can see the Mosaic 88, which covers all of the spectrum, only with a few small gaps to allow for the lasers. On top of that, so it has 6 side scatter detectors. And what is a quite unique feature is that the emission is detected up to over 950 nanometers. And what you don't always see in all instruments is that gap at 800 nanometers, but that is to allow for the infrared laser. And I'll come back a little bit to that. So as I said, so we have invested heavily in spectral cytometry at our facility. And that is because we think there's a lot of advantages to spectral cytometry. So first of all, of course, you can distinguish highly similar fluorochromes. You can go to huge panels. But something else that we really like is you can do autofluorescence extraction. And the instruments are fairly easy to use because you don't usually have to do gain or voltage optimization. And on all of these 3 points, I'm going to provide some data because we, of course, tested. We think these are advantages of spectral cytometry, but we really wanted to test how the mosaic performs on all of these points. So first of all, how does the mosaic distinguish highly similar fluorochromes. So what we did is we tested 3 notoriously difficult combinations of fluorochromes, so BV421, Super Bright 436, and eFluor 450. Here you can see in a traditional spectral viewer that the emission is very similar, and using the detector on the LX, it would be impossible to distinguish. FITC and BB515 are even more similar, and then there's also APC and Alexa Fluor 647, which are also hard to distinguish. And I think that the first one these may look a bit more different, but this is actually a combination that doesn't work even on some spectral cytometers. So I just showed you the spectra on a conventional spectra viewer, but these are the normalized spectra as we recorded on the mosaic. You can see that there is small differences in the emission of the 3 fluorochromes here, of FITC and BB515, and the same for APC and Alexa Fluor 647. But still, it looks very similar. If you look at the similarity index, so for BB515 and FITC, it's even 0.98. So that is really at the limit of what you can distinguish. So what does that look like? So we took some mutually exclusive markers, so CD19, here we have CD34, CD4 versus CD8, but you can see all of these markers actually unmix really well. So there is a little bit of spread error, but it's not that severe. And if you want to gate any of these fluorochromes, if you want to gate any of these cell populations, so there's not many CD34 positive cells here, but even when there is not many of these cells, I can really, with high confidence, select these cells and I gate them and analyze them. But in this case, so I can unmix these fluorochromes, but when I see this type of data, I always think, well, should I really do that? Because these panels, this is not something anyone would ever use. You would try to spread your fluorochromes a little bit. No one's going to use a panel with only these 2 or 3 fluorochromes. So to go to a bit more realistic, to a more realistic use case, so we filled up the spectrum a little bit, and we use the same combinations of fluorochromes, but we actually put in a lot of other fluorochromes that have a lot of interacting dyes, but still no co-expression, just to make it a bit easier to look at the data. So here, that's the 3 dyes, so BV421, Super Bright, and the eFluor 450. They're here, but you can see there's a few secondary peaks from some BV dyes, and this one's the autofluorescence. So there's a little bit of interaction here. For FITC and BB515, we didn't do this whole exercise because there's not enough dyes that interact with those, but for Alexa Fluor 647 and APC, there is a lot of dyes that interact. So we use, for example, PE Sci5, which is notorious, but also APC tandems, BUV 661 and BV 650, which are all notorious to have a secondary peak in the emission spectrum of APC and Alexa Fluor 647. And you can actually see that there's a secondary peak there. So these are actually plots that you get when you unmix your data. So you get these normalized signatures, and you also get the similarity index. So as you can see, the similarity index is not all that terrible. So you can definitely discriminate all of these markers. But the similarity index doesn't actually tell you anything about the reduction in stain index, for example. So we compared, so if we go for either the simple panel or the complex panel, so the simple panel is always on the left, and then the more complex panel on the right. And especially for that first combination of BV421, the Super Bright, and the eFluor, it actually still looks good in the more complex panel. There's very little difference. The unmixing is still pretty good. There's no inflation of the negative peak. But if we look at the combination of Alexa Fluor 647 and APC, which has a lower similarity index, but there's actually a lot of spread error occurring. And that comes from all those secondary peaks. So you can see the red arrow that negative population is really inflated, so you do lose a lot of resolution. We can still separate that really small CD34 positive population, but the TCRV alpha 7.2 population gets a lot harder to discriminate. So basically, you can definitely unmix these highly similar fluorochromes. I would still recommend only to use them if you have no alternatives. And if you use them, it really takes some careful panel design. So you really have to make sure that you use very bright markers and make sure to put these markers on to make sure that they're mutually exclusive, so not co-expressed on the same cell. All right, then the second part that I mentioned is autofluorescence. So all biological samples contain compounds with fluorescent properties. There's a lot of sources for that. So some common sources are things like tryptophan, NADPH, but also collagen, elastin, or maybe even some sample formaldehyde or phenol red that is present during sample processing. These all can lead to what we call autofluorescence. And it can sometimes be difficult to distinguish autofluorescence from the true signal that you do want to measure. So to test how the mosaic handles this, we try to use a complex sample. So a sample that may have even more than one autofluorescent signature in there. And in this case, it's a very common sample type because it's a red blood cell lyzed whole blood. And we stain this panel with a lot of fluorochromes that actually emit in the same spectrum as autofluorescence as where autofluorescence is usually found. So normally, again, this would be a terrible panel to use, but especially so a FITC, BUV 496, BV 510, the C Fluor, BV 570. These are all well known to be in the range of where you expect cellular autofluorescence. And then there's some lineage markers that are really in the far infrared, which should not suffer from autofluorescence. So just to compare, so we ran an unstained population in CytoExpert for Spectral, and well, it looked were able to identify 4 different populations. And if you look at the normalized signatures, you can see that actually, so these are the 4 populations. So there's one that is really, really different. So that's on top. It's the red line. And that was actually eosinophils, whereas the other 3 lines are neutrophils, lymphocytes, and monocytes. If you look similar. And I made some dotted lines to really show, if I compare it to the panel, that it's really that these fluorochromes really emit in the same range as the where you find the autofluorescence. So looking at the so you can also look at the similarity index of your unstained, so your autofluorescent populations. And there actually we see a few points where the similarity is more than 0.99. And that is what you get between neutrophils, monocytes, and lymphocytes. So usually that means that this signature, that the similarity is so high that you don't need all 4 of them, you only need to keep 1 of them. And then if you keep 1, you want to keep the brightest population. So that really leaves us with only 2 autofluorescent signatures left for this panel. And in this case, that was the neutrophils and the eosinophils. So what does it actually look like? So here's a plot. So this is gated on the granulocytes. Blue is the neutrophils and red is the eosinophils. If I don't know any autofluorescence extraction, we see a pattern that does not really make any sense. So both neutrophils and eosinophils are CD6-6b positive, but the eosinophils actually look like they're CD16 positive, which from my experience, I know they should not be. If I look at HLA-DR and CD4, both the neutrophils and eosinophils seem to be slightly positive, but the eosinophils look very positive. They shouldn't express these markers. Sorry, CD4 actually. If I look at CD8, it's even worse. Actually, the eosinophils dive deep into the negative. So it seems like they have a negative expression of CD8, which is just impossible. So what happens if I add 1 autofluorescent population? So in this case, I add the neutrophil signature to the unmixing, and then actually things look a lot better. So the eosinophils become CD16 negative, although they dive a little bit. If you look at the MFI of this, it's actually negative, so that's not great. The HLA-ADR and CD4 start to look better, and the CD8 looks a little bit better, so a little bit less negative perhaps. But then actually when I add a second population, so a second signature in the unmixing, so I add both the neutrophil and the eosinophil signature in the unmixing, then everything looks like it should. So the eosinophils are negative for CD16, but not with a negative MFI. They're negative for both HLA-DR and CD4, and they're nicely negative for CD8 as well, but not diving into the negative again. So what happens if I add a fourth population? Well, not much. Actually, adding more autofluorescent populations in this case does not improve the unmixing. It also is not expected to be, because the signatures of the lymphocytes and monocytes I would put in there, but they're not in the graph. So is more autofluorescent signatures always better? Well, no, not necessarily. So this is the same panel, but then for the monocyte subsets. So this is gated based on forward cyclic scatter on monocytes, and you can distinguish based on CD14 and CD16. You can the classical, intermediate, and non-classical monocytes. Without any autofluorescence completely on the left, you see that all cells appear positive for CD16, which especially the classical monocytes should not be. If I add one autofluorescent signature, the cells are nicely where they should be. With a second one, also the classical monocytes are negative for CD16, and even it seems like the population is a bit more tight. But then if I add all four of the autofluorescent signatures, you can actually see that the classical monocyte population is swelling up a little bit. And if you quantify that and you look at the variance in that population, it actually increases with 4 autofluorescent populations. So this is a very simple panel, but if you have a very large panel, I expect that this will be more of an issue. So basically the take-home message from this is that you can use more autofluorescent signatures, but you should really be careful how many to use, because you can use too many. Then is autofluorescence always a bad thing? Do I always need to extract it and get rid of it? Well, I would definitely extract it, but you can actually use the autofluorescence for a useful purpose, because these eosinophils, they really had a unique spectrum. And so these unstained 1 and unstained 2, these are the this is the autofluorescence that is extracted from the sample. And there I can see, so in red I gated my eosinophils, and actually I can separate the eosinophils based only on their autofluorescence, and especially if I plot the two together, and that means that I might not even need an antibody for this. And I know that there are some users in my facility that don't bother using antibodies targeting eosinophils anymore. They just use the autofluorescence to identify these cells. All right, so then the third part, do we need to optimize the system? Does it require a lot of work? So for that, we ran OMIP 104, which was designed by Joost Lamboy. His picture is on here. He's a PhD student here at the Leiden University Center for Infectious Diseases. And he designed a 30-color panel that was aimed at broad immune phenotyping of metabolic tissues of mice. So this is basically liver and fat samples. And his group has a focus on macrophages, so they really zoomed in on that. The panel includes activation markers, and it also includes a lipid tox. So that's a lipid loading panel, a lipid loading marker. So it's, Joost always says, well, it's only 30 colors, but it is a very complex sample. And with the activation marker and the lipid loading, it's actually a fairly complex panel as well. So initially, this panel was designed for the Cytek Aurora, but we decided to just run it on the Mosaic and without any optimization. And actually, it worked beautifully. So we were able to identify all of the immune cell subsets that we were able to identify before, and it was little to no difference to the original publication. So the gating really worked well. So this is just for identification of all the cell types. So as said, so it's fairly broad: B cells, neutrophils, T cells, but really zooming into the different monocytes, dendritic cell, and macrophage populations, where we can, for example, see Kupffer cells, resident Kupffer cells, and yeah, that worked really well. Also, the activation and metabolic markers. So we were definitely able to quantify all of these markers and the lipid load on the different immune populations. And the only differences that we were able to find with the original publications were all due to the mice being the cohort that we used the panel on was slightly different from the original publication. That these mice were a bit more diseased, so the expression was higher. Then for this panel, Joost also required quite a lot of autofluorescence extraction. So, and in this case, he actually used 4 autofluorescent populations, which led to the optimal unmixing. So you can see in a normalized spectrum, you can see that these 4 populations actually have fairly different signatures. So the highest similarity is 0.96, but I even see a similarity of 0.34, which means that it's very different. And again, so on the right, you can see that if you unmix it with only one autofluorescent signature, the red circle indicates this huge tail going into the negative, and that is a clear indication that there's something wrong with your unmixing, or at least that there's some signal that is not taken into account very well. But then if we unmix with 4 fluorescent signatures, autofluorescent signatures, then the unmixing looks beautiful. So that's on the top. All right, so yeah, the conclusion from OMIP 104 on the mosaic was that it was actually really easy. So we were able to transfer the panel, required no optimization at all. Although I think that if we move forward with this, we definitely can improve the panel. We could still retitrate some of the antibodies to get rid of some, to reduce the spread error even more. But also the mosaic allows you some options that you don't have on all other spectral instruments, because the mosaic, well, there's the 808 nanometer laser in there, and we don't have any fluorochromes excited by this in the panel, but we could definitely switch to using some of those. In addition, as I mentioned, so there is the ability to detect fluorescence with a wavelength of between 850 and 950 nanometers. And so we would be able to use fluorochromes that excite in that range. Now, there's not many fluorochromes available right now on the market, but I already have seen some data that these fluorochromes are being made and they will enter the market. Then the last bit of data that I want to show is also unique for the Mosaic 88. So, and that is about the 6 different site scatter detectors, which is a really unique feature for this instrument. When I asked people from Beckman Coulter, like, well, what would I use these site scatter detectors for? They basically told me, well, we're not sure yet, go figure it out. So that's what I did. And basically in every panel that I ran, every sample that I ran, I just decided I'll make an n by n plot with all my side scatters and see if there's anything interesting popping up. And already in that one experiment where we measured whole blood, we saw something interesting. Because here there's an n by n plot, and usually, so for example, on the bottom, if I usually that's somehow I would expect my scatters to look like. So you have a 45-degree angle, so that means that the scatter is exactly the same for both laser lines. But if you look a little bit more to the top, you see that not all populations are on a 45-degree angle. So there's actually a population appearing on the right side. And it's something that is very high in side scatter. And it's most prominent in the red and infrared side scatters. So again, we made a small panel and we decided to see which cell type this could be. So we were able to identify neutrophils, eosinophils, but because they're granulocytes, well, let's also look at the basophils, PDCs, B cells, T cells, monocytes. And then actually you can see that in red, that's your eosinophils. So from when we go from UV, the separation is not good. Violet, blue, yellow, red, and infrared. The separation between your eosinophils and your neutrophils gets better when the wavelength increases. We also tried, so how is this just as good as doing a staining with, for example, CD16 and CD66B? And although we only measured a few samples, the correlation was near perfect. So that means that you can use this infrared side scatter and maybe also the red to identify your eosinophils completely label-free. So that takes me to the conclusion of my slide, and that is from our facility, our humble opinion on the mosaic. We think it has quite a lot of pros because it's really just a CytoFLEX LX, but spectral. If you love the CytoFLEX, you'll love the mosaic. In our hands, it's been easy to use and stable. It was really easy to get the autofluorescence extraction to work. And all of those plots that I showed you, so with the normalized signatures, the similarity indices, they really help you to get the best out of your unmixing. So then there is the infrared laser and the ability to detect infrared light up to a far longer wavelength than on other instruments. So that actually allows you to expand your panels with relatively easily. And then last of all, those 6 side scatter offer new label-free applications. So of course, there is a few cons, and I think you should, I can mention those as well. So there's still some software features that are on my wish list. So I would like a bit more of an autofluorescence finder that helps me to find those different autofluorescence signatures. So now I will have to do all of it manually. It's doable, but some help with that would be appreciated. And setting up plates and unmixing is a little bit cumbersome. But I have to say that I have already seen multiple software updates since we received the instrument, and the usability has improved quite a bit. And then about the capabilities of the instrument, well, you saw that small gap at around 800 nanometers. So that means that if you really love some of those dyes at 800 nanometers, your sensitivity will be slightly. It's definitely still possible to detect everything at around 800 nanometers, but you do have to take into account for your panel design. And taking all of this together, we really like the instrument, and we actually think that it's performing better than some of the instruments that are already available on the market, while we only had a beta test version. So then that brings me to actually the most important slide of all. So the acknowledgements, because there's a lot of people that I have to thank. There's a people from Beckman Coulter that really were kind enough to allow us to test the instrument. And then there's a lot of people from the LUMC that really helped to keep the instrument up and running. So it's all the people from our facility, and with special thanks to Joost, because he ran all the samples for the OMIP 104 experiment. All right, so that was my last slide, and then I'll be happy to take your questions.
All right. That was an amazing presentation. Thank you very much, Tamar. Let's take a look to the question that we have in the chat. How about that? Let me see what we have here. So first question for you. What are the practical advantages of having 2 independent detection systems, conventional and spectral in one?
So I think it depends a little bit on the use case. So in our case, we have so many users and so many instruments that we have dedicated instruments for spectral and conventional. But especially in a smaller facility, there there are use cases where you really need a conventional instrument, and then of course it's much nicer if you just have to purchase one instrument that has both conventional and spectral. One of the examples that I know of is, for example, if you do ratiometric measurements, for example, I know there's with some FRET measurements in York, they were unable to do those in the spectral mode, but they could do it in conventional. So then you have both of those in one instrument, and that can definitely be beneficial.
Right. So the next question is actually related, because it's how often do you switch from conventional to spectral? But you say that you actually keep it on spectral, right?
Yes. So we have moved to switching it once a month and run some beads on it. But because after the first time I tried spectral cytometry, I didn't go back to conventional unless I really had to. So we really rarely move it back to conventional.
I see. Thank you. Next question is a little bit more technical. So how do you determine when to use highly similar fluorochrome? Even if the similarity index is high, like more than 0.95, in what situation would you recommend avoiding fluorochrome with high spectral overlap?
So I would recommend to avoid it whenever you can. So if you can avoid using that combination, avoid it. Your data will look much better if you don't have these really high similarities. However, it's more a case of if you have to use them. So if you go beyond 40 colors, you'll have to use a few fluorochromes that really have that high similarity. But then you have to be really selective. So you really make sure that the marker is expressed exclusively on the two, so that the two fluorochromes are never present on the same cell. And usually you want to take like a very unique cell type. So if you do broad immune phenotyping, something like a plasmacytoid dendritic cell or a basophil, which you gate out pretty early, usually doesn't express much of the markers that the other cells do. So then you can do it. Yeah, so basically only if you really, really have to. Otherwise, I'd really recommend not to use that combination.
Yeah, fully agree. So another question is, oh, that's very interesting, is did you do a gain tracing on all the channels? Is it needed? How do you handle all the data?
So no, we didn't do a gain tracing. So the mosaic comes with assay settings, which actually have been optimized to minimize the spread between the fluorochromes that are available and that were tested. So for example, if you look at the combination of PE and PE size 7, if you would keep the gains all the same, you would actually get quite a lot of spread from one into the other. You get a lot of spread error. But by balancing those gains, you get much less spread. So I try not to touch the gains at all. There is cases where, for example, if you don't look at fluorochromes that are coupled to antibodies, so for example, you look at naturally occurring fluorochromes, then you might have to do a gain tracing. Usually, I still try to do the gain. If I do a gain tracing at all, I try to do it with all channels at the same time. So I just increase the gain of all channels by 10% or by 20% or something like that. So that means it's much less work. And for example, for the OMIP 104, we didn't do any gain tracing at all. And handling all the data, well, that's a bit of it's not that much of a problem. So it's a lot of flow cytometry data, but if you compare it to like a microscopy facility, it's still peanuts. So it's not all that much data. So I guess in that respect it's okay, but we do see a lot of users that are measuring like for maybe 5 hours, and then they spend 3 weeks analyzing the data. So you see that your users spend much more time analyzing their data than collecting the data.
Yeah, good point. Have you ever run dissociated tumor samples? Lung, for example, did the autofluorescence subtraction help?
So I haven't on this instrument, but I have on other spectral instruments. So I think any tissue biopsy will greatly benefit from autofluorescence extraction. And then especially the multi-autofluorescence extraction. So but it all depends on what you're looking at. If you're looking at both T cells and tumor cells at the same time, those two have a different autofluorescence signature. So then you'll have to include the autofluorescence of one and the other in your unmixing. If really you're only looking at T cells in that dissociated tissue, then it might not be as useful. But especially in those complex samples, I think it usually really is.
Thank you. Let me see. We have quite a few questions. That's amazing. Thank you, everyone. So, are the original channels of the CytoFLEX incorporated, or are they bypassed completely?
Yeah, they're bypassed completely. So you have to switch the optical fiber from conventional to spectral. So it's completely bypassed. So you can't use the conventional the data from the conventional detectors. On the other hand, that would mean otherwise it would mean that you lose signal.
Yeah. Yeah, the detection system is the module is your new detection system practically.
Yes.
So this is an interesting question. Could you please elaborate a bit on why we can see negative fluorescence for some fluorochrome after a mixing? Does it always indicate that there is something wrong with the unmixing?
So it may indicate that there's something wrong with the unmixing. It is also possible that there is a lot of spread error. So you see the same thing in conventional, but in spectral, especially if those instruments are really sensitive, the spread error actually becomes your enemy, especially in those like 40 plus parameter panels. And you get spread error that the brighter your fluorochrome is, at some point you see spread appearing. So half of that will register as something negative. But if it really looks like that, then your unmixing is perfect. It's just that maybe your panel is not ideal, because with careful panel design, you can prevent that spread error. So it doesn't always indicate that there's something wrong. However, if you really see those negative populations, what it often means is that there is a signal in your data that is not accounted for by your unmixing matrix. And in practice, that usually means that there is something in there that you didn't tell the system exists. And nine times out of 10, it means there is an autofluorescent population that you haven't accounted for.
Very good point. Let's move to your size scatter data. Okay, this question is for the granulocyte multi-site scatters live gate. Have you also compared the results with a normal granulocyte live gate, like size scatter areas versus forward scatter area without the PBMCs?
Yes, I actually have, but then I just started gating based on CD16 and CD66B. So in my experience, the blue side scatter, which is the most commonly used one, versus forward scatter, that doesn't separate your neutrophils and eosinophils. But the deeper the side scatter goes into the infrared, the better the separation becomes.
There are two questions that I think I can read both and they are probably related. But so have you combined your side scatter data and your autofluorescence to even better characterize eosinophil? That's one question. And then the other is I plan to acquire the mosaic option for my 4 laser CytoFLEX S. It has only 4 additional scatter detectors. Could it be worth for the label-free discrimination of high autofluorescent cell subset?
So, so for the first question about the side scatter and autofluorescence, no, I haven't tried it, but well, the side scatter already does the trick. And I know there is a few users in our core that don't add antibodies against eosinophils anymore. They just use a unique autofluorescent signature. So I could use both to characterize them better, but I think either of them is good enough to identify the eosinophils. And I don't really see a lot of heterogeneity in the autofluorescence and the side scatter. So I don't expect to see separate populations like that. So about the mosaic, the 4 laser CytoFLEX S for the label-free discrimination. So it depends on what you want to do. So it seems the eosinophils are really unique in their behavior with the infrared side scatter. So I'm not, depending on what type of sample you want to measure, it might not help you that much. And if you want to do label-free discrimination of cell subsets based on, and they're really highly autofluorescent, a 4 laser system will really help. Most of the autofluorescence is seen on the UV laser, so that's where you get the best signal, the best separation. But already in violet and blue, you are able to discriminate a lot of different populations, and it's usually just a matter of how well the separation is. So in UV versus violet, it will probably work best. But then if you have violet versus blue, it will still work. Just, yeah, the separation is just not as big.
Thank you, Tamar. You have excellent presentation. Thank you. And he's asking, what is the reason for switching to conventional once a month and run some beads?
For me, it's really just we actually run multi-peak beads for all our instruments. So we do this to monitor if the instrument is still performing okay. And since we weren't using the mosaic at all in conventional mode, well, if something goes wrong with the instrument, I don't want, if we switch it, it means there's a user that has a specific question and probably has an urgent need to use this system. And I don't want to find out at that moment that the instrument is not performing well. We haven't had problems so far, though.
That's good. Next question. Oh, that's a good one. Should we do single color unmixing for each experimental run, or we can use it for multiple runs over the months?
So this depends on how stable the instrument is. So for 1 month, usually I recommend to run the single stains only maximum once a month, because it's better to spend a lot of time to make really good single stains and then reuse them than using suboptimal single stains every time. And in my experience, the instrument has been very stable. So if you unmix with single color controls from more than a month old, the unmixing is usually really fine. I haven't tested it up to years, but so there will be a limit, but you can definitely last 1 month with your single stain controls.
Okay. So new question. Okay, so do you have a shared experience on the BD new fluorochromes, such as the real yellow, the real blue dyes that are very bright? And is asking for concentration titration that will you recommend to stain human PBMCs?
So I can't recommend any, standard titration. What I do notice is that brighter isn't always better. So sometimes, I've always been taught that when you do your titration, you go to the point where you have the maximum separation. The only problem is that if you have really complex panels, is that you get all that spread error.
Mm-hmm.
So sometimes actually your data looks a lot better if you go for a lower titration that leads to less spread error. And then you can actually separate your populations much better. So my recommendation is to titrate fairly low. And if you see that spread error, see if you can titrate it even lower. Of course, there is one small risk with not titrating at saturating concentrations, but usually you can get away with that.
Yeah. Okay. Yes, is gain iteration needed for really bright, like staying on bright fluorophores? Like is gain iteration really needed for bright fluorophores like proliferation dye, like the CFC, the CTV, PKH26?
Yes. It depends though. On freshly stained samples, you definitely need to take down the gains quite a bit. If it's like 3 days old, so because you lose quite a bit of fluorescence in those first few days, it's often you don't have to you don't have to reduce the gains that much. But yes, if it's really bright, you have to do that. We have analyzed some plankton, for example, and there we really needed to take down the gains to like 1% of the standard settings.
Yeah. So a quick question about the switch from going back to switch from conventional to spectral. So how easy is it to switch? Is it something that you do like in the middle of the day?
It is really easy. So you could definitely do it in the middle of the day. I think so. You just have to unscrew the optic cables, screw them back in, and then you run a QC on either conventional or spectral. So whatever it is you're using after that. But I think it's like 10-15 minutes and you're ready to go.
Yeah, super fast. Let me ask you another question. Like this is from me, but like now during all these months that you've been using Mosaic, what was the most interesting sample that you have run?
That was definitely plankton. So we got a visit from two marine biologists who basically just scooped some water, some seawater. So they do research on viral marine viruses. So we were able to see those marine viruses and actually check with, for example, the different scatters, which scatter worked best on the viruses. And something what I should have known, but I didn't, and that it was like a PE-like signal in a very small population of plankton. And then I was like, wow, that signature looks almost like PE. And then they looked at me and were like, well, it is PE because PE comes from plankton. Like, okay. I learned something that day.
That's funny. We have a couple of more questions. So when taking down laser gains, can this be done independently or do all laser have to be taken down the same extent at the same time?
So you can change the gains on every detector separately if you want, and you can do it either per detector, you can do it per laser line, or you can do it for everything. So it's really whatever you like. I'm always a bit hesitant to play with the gains, and that's
Right.
mostly because messing up those assay settings, it's really difficult, and I think it's really difficult to. Well, you have to do a gain iteration on 82 channels or 88 even, and then you have to take into account the different spread errors, etc. So I try not to do it, but you can do it if you really need to.
We have a last question. Could you compare of Mosaic add-on with Cytec Aurora platform in terms of sensitivity resolution?
So my institute doesn't allow me to do one comparisons, unfortunately. So I didn't get the data, so I can't really say that anything clear about it. What I can say, so we showed the OMIP 104, and we compared the data, like, so basically just eyeballing, were we able to identify all the populations, etc. And that worked basically the same as with the Cytek Aurora.
Perfect. Oh, there is one more. Which are the difference between the two algorithms for their mixing?
So I can't tell you anything about the math behind it, because I don't understand that. I understand the ordinary least squares a little bit nowadays, but the hybrid Poisson I find a bit difficult. I tried to unmix all my data with the two algorithms, and I haven't seen any differences. I have, however, seen example data where the controls were not optimal. So, for example, and I think there was a specific example where NK cells were measured, where you have a CD56 bright population and a CD56 dim population, and the gate for the single stain control was set on the dim population. And then with the ordinary least squares method, the CD56 high population went like really into the negative. So it's a very specific pattern that you get. And with the Poisson, it actually looked good. And that was a panel where in a few cases it worked better. So it seems like the hybrid Poisson is a bit more forgiving for user errors. And of course, we all like to think that we all have the perfect panel, but I think in real life, quite often your panel is not perfectly optimal. So it might be very useful there. But I really have to be honest that that I haven't seen much difference yet.
Yeah, adding to that, just from other customer experience, I can just say that the Poisson hybrid is an hybrid between the LSM and the Poisson. Poisson has been proved to help with the spreading, right? So minimizing the spreading. We do have a few data that show a difference between the two, and a lower spreading in specific panel. But then going back to you, right, is like, let's say that the two algorithms works very well, both of them. The trick is to use them both and evaluate your own panel on your own sample, because sometimes you can see an improvement and that can be helpful, and sometimes they can be very similar. Yeah. Okay. I think that we finished all of the questions that we did have. And I just want to thank you, Tamar, for your time. Thank you, everybody that joined in and spent this hour with us. It was fun, and thank you for all the questions. That were really good. Thank you, everybody.
Thank you as well for the opportunity, and thank you all for watching and all the nice questions.